Hello everyone, myself Dr. Ranjana Gogoi, Associate Professor in Statistics, working at Gorgaon College. Welcome all of you to today's presentation. Today I am going to present the topic Simple Linear Regression Model. This presentation is designed for the BSc 6th semester non-CBCS Statistics major students as well as BSc 4th semester CBCS Statistics Honours students under Dibrugarh University. Linear model is highly innovative tools in statistics, those who practice applied statistics and data analysis. The linear model involves the simplest and seemingly most restrictive statistical properties: independence, normality, constancy of variance, and linearity. However, the model and the statistical methods associated with it are surprisingly versatile and robust. More importantly, mastery of the linear model is a prerequisite to work with advanced statistical tools because most advanced tools are generalizations of the linear model. Thus, the linear model is central to the training of any statistician, applied or theoretical. So, in this presentation, it is tried to develop the basic theory of simple linear model for regression. In simple linear regression, we attempt to model the relationship between two variables. For example, height and weight of people, temperature and the output of an industrial process, etc. For a linear relationship between two variables, we can use a model of the form y equal to beta naught plus beta 1 x plus epsilon, where y is the dependent variable or response variable and x is the independent or predictor variable. The random variable epsilon is the error term in the model. Here, error does not mean mistake but is a statistical term representing random fluctuations, measurement errors, or the effect of factors outside of our control. Here, the data is collected for n observations and hence we get n equations of the form yi equal to beta naught plus beta 1 xi plus epsilon I, where I takes the values 1, 2, 3 up to n. The designation simple indicate that there is only one x to predict the response y. And the linear means that the model is linear in beta naught and beta 1. That is, the power of beta naught and beta 1 is 1. To complete the model, the following additional assumptions are made. The first assumption states that expectation epsilon I equal to 0 for all I, or equivalently, expectation yi is equal to beta naught plus beta 1 xi. So, the assumption 1 states that the model 1 is correct, implying that yi depends only on xi and that all other variation in yi is random. Assumption 2 states that variance of epsilon I equal to sigma square. So for all I, the variance of epsilon is constant, that is sigma square, or equivalently variance of yi is equal to sigma square. So assumption 2 asserts that the variance of epsilon or y does not depend on the value of xi. This assumption is also known as the homoscedasticity or homogeneous variance or constant variance. Under assumption 3, it is seen that covariance of epsilon I, epsilon j is equal to 0 for all I is not equal to j, or equivalently covariance of yi, yj equal to 0. That is, the epsilon variables or the y variables are uncorrelated with each other. is the correlation between yi and yj is equal to 0. The y variables or the epsilon variables are independent as well as uncorrelated. So here we have seen that each assumption has been stated in the terms of epsilons or the y's only. Now our problem is to estimate beta naught, beta 1 and sigma square. We have with us n pairs of observations xi, yi, I from 1 to 3 up to n. So we can estimate beta naught, beta 1 and sigma square with the help of least square method. So by least square method, we minimize the sum of the squares of the deviations yi minus yi cap of the n observed yi's from their predicted values yi cap equal to beta naught cap plus beta 1 cap xi. So here beta naught cap and beta 1 cap are the estimated value of beta naught and beta 1 respectively. So this deviation is somewhere it will be positive or somewhere it will be negative. So to ignore the signs of the term, we can take the square values and take the summation, that is summation I from 1 to n yi minus yi cap whole square. And this is nothing but summation I from 1 to n yi minus beta naught cap minus beta 1 cap xi whole square. Now to find the values of beta naught cap and beta 1 cap that minimizes epsilon cap dash epsilon into, we differentiate with respect to beta naught cap and beta 1 cap separately and set the results equal to 0. This is the procedure of least square method. And we get these two expressions 3 and 4, and after simplifying these two expressions 3 and 4, we get the values for beta 1 cap and beta naught cap. Here you see this xi into yi summation I from 1 to n. So we can calculate this xi into yi from our given data, the sample, and take the summation I from 1 to n. Similarly, we can calculate x bar and y bar from the given data, and n is the number of observations. And in the numerator, we can calculate also xi square and take the summation for all n observations and n into x bar square, and we can find the value of estimated value of beta 1, that is beta 1 cap. And similarly, we can find the value of beta naught cap, which is equal to y bar minus beta 1 cap x bar. Now, to estimate sigma square, we use the definition of variance, that is sigma square equal to expectation yi minus expectation y whole square. By assumption 2, sigma square is same for each yi. It is a constant variance. So by y, we use yi cap as an estimator of expectation yi. So we can estimate sigma square by an average from the sample as s square. S square is calculated from the sample observation. This is the sampling variance, and here denominator is n minus 2, because in the numerator you see this is the yi minus yi cap. This is nothing but yi minus beta naught cap minus beta 1 cap xi, and we take the estimated value of two parameters beta 1 and beta naught. Hence the divisor is n minus 2, and this summation is nothing but sums of squares due to error. This is the error term actually. Yi minus yi cap is the error. So this is the squared value and this is the sum. So it is known as sums of squares due to error. SSE is called residual sum of squares or error sum of squares. With n minus 2 in the denominator, S square is an unbiased estimator of sigma square. This is the expression. So we divide n minus 2 in 7 instead of n minus 1, as S square has two estimated parameters. That is beta naught cap and beta 1 cap, and should thereby be a better estimator of expectation yi than y bar. So after estimating beta naught, beta 1 and sigma square, our next step is to go for hypothesis testing and building of confidence intervals for beta 1. Hypothesis testing about beta 1 and are more important than the hypothesis about beta naught. Since our first priority is to determine whether there is linear relationship between y and x. We will discuss about hypothesis testing and confidence interval for beta 1 in the next video. Thank you.